Hello and welcome. My name is Michael Carney and I'm an applications engineer at EWI. I will be presenting on behalf of the project team on the topic of robotic arc directed energy deposition, additive manufacturing, test bed overview, and propeller build demonstration. At this time, I would like to acknowledge that the content being presented was developed as part of the National Shipbuilding Research Program, Advanced Shipbuilding Enterprise, Research Announcement, Project 2019-375-004. The large-scale multi-process robotic gantry DED system was commissioned on July 2020. It is a pre-engineered commercial off-the-shelf system. The system has a working range of 8 feet 2 inches high by 14 feet wide by 30 feet long. It has a 60 kilogram ABB IRB 4600 robot that is capable of multiple processes. It is an 11-axis system with a 1-ton tilt-turn positioner. There's also a sensor platform for development of quality control and part certification technologies. This creates a unique resource for prototyping metal DED AM structures and components. This system is available for large-scale DED application development. The welding systems currently integrated into the system are a Fronius TPS 500i CMT system and a Lincoln Electric S500 system. In addition, there are also welding accessories such as a Benzel torch maintenance station, which is shown in the lower left, a Benzel torch exchange station, which is shown in the lower right, an additional wire clip station at the base of the robot, and an ABB bullseye for an accurate tool center point. In addition to welding, the system also has metal working processes driven by a push-corp 5 horsepower spindle with active compliance and a tool changing station capable of grinding, brushing, and deburring. The images of the system are shown to the right. The monitoring sensors integrated into the system include weld data acquisition, a Melt Tools weld pool monitoring camera, and a Micro Epsilon TIM 640 thermal imaging camera that can indirectly measure the surface temperature in a range from -4 to 4,442 degrees Fahrenheit, which can then be used to control inner pass temperature. Lastly, the Benzel TH6D-GF sensor can seam track, measure profiles, and document, and can be used with both welding systems. These sensors are shown to the right. The propeller blade build is a single stainless steel high skew propeller blade that was produced using 0.045 inch diameter ER308L SI wire on a type 304L build plate that was 1 inch by 24 by 48 inches. The dimensions are shown in the lower right. The width is approximately 20 inches mid-height, and the blade is 42 inches tall. This pictogram is courtesy of Autodesk and shows the 10 additive build categories. These increase in complexity from 1 being a linear extrusion to 10 being artisan. The propeller blade being produced is a build category number 6. This pictogram is again courtesy of Autodesk, and it shows the digital data workflow in 7 steps. Step 1 introduces the CAD component. Step 2 is where you preform or change the component for AM. Step 3 is where you set up the component in PowerMill. In this case, it is set up in a chuck. Step 4 is where you introduce the trajectory. Step 5 is where you decorate or add specific process conditions to the trajectory. Step 6 is where you sequence the build. Here you can add items such as wire clipping or active cooling. And step 7 is where you simulate your build and output the NC program or robotic code. Here the propeller blade is being presented in the digital data workflow. No modifications were made to the CAD model. In step 5, a boundary was utilized around the tips of the blade to change to a lower travel speed. In step 6, both a wire clip and intrapass temperature check were utilized. Here the build strategy is presented. It is a 4-axis build on a flat build plate. 3 builds per layer with staggered integral starts and stops with a width of approximately 3/4 of an inch. An offset toolpath strategy was used to solve the path plan. The design and path plan are shown in the top, and the simulation model and cell are shown in the bottom. Here the build is shown in the lower left and right. The build had very consistent build profiles and visually appeared to have complete fusion. This is shown up close in the upper right-hand corner. Here is a time-lapse video of the build to date. Next step for the propeller blade build is to complete the remainder of the build. Once this is complete, a 3D scan of the build will be completed and compared back to the CAD model. Thank you.